I'm Matt Swartley with Chariot Solutions, and I would really like to thank all of you for attending the conference today. I'm here to introduce you to Stewart Smith, who is the head of consumer augmented reality at Unity Technologies. He has also worked with renowned hybrid studios, won industry awards, and even collaborated with Erno Rubik to create Beyond the Rubik's Cube Traveling Expedition. And I would highly recommend you checking out that website when you have time. Today, Stewart is going to speak with us about quantum computing, including details about his open source passion project called Q.js. So please welcome Stewart Smith.
Hey there, let me share my screen so that I can start showing you what I'm talking about.
All right, thanks for.
Oh, let me share that with sound. Okay, fantastic. Are we good to go? We can see a triangle and you can hear my voice?
Looks great.
Fantastic. All right. So let's get started here. Quantum computing is going to change the world. Not tomorrow, but over the course of a generation. So young children growing up now, by the time they're grandparents, they will have seen this change take place. So this is just like folks who were born during the era of those first computers. Now they carry around these supercomputers in their pockets called smartphones, and we don't really think anything of it. I don't think people will be carrying around like quantum computers in their pockets. I'm just saying they'll be cheap enough, ubiquitous enough that they're commonplace. So if that's the case, you ought to know something about quantum computing. What is it? What's exciting about it? And so on. And by the end of this talk, you are indeed going to know some things about quantum computing. Yes, my friends, this is quantum computing for hapless dreamers. So why the hapless dreamer part? I'll get to that in a moment. But first, I know some folks like to live tweet these talks. So this QR code links to my Twitter profile. So you can mention my Twitter handle and direct all of your criticism and questions there. So my handle is just Stewart Smith. And you replace that A with an underscore and you're golden. I'll share more contact info at the end, but I figured it's always a good idea to take care of the real-time folks early in a talk. And also I want to give a shout out to my good friends watching from England, New York, Arizona, California, Australia, all points beyond. So back to the task at hand here. All right, so why hapless dreamer? Well, hapless dreamer, it's a bit self-deprecating, of course. I say that because I was made to feel like a hapless dreamer in school. I don't know, anyone else feel a little bit lost in school at times? I know I'm not alone on this. Perhaps the positive spin on hapless dreamer is I like to see the connection between things, between subjects, between genres, totally disparate thoughts. And that's led me down some really exciting paths. So maybe you're watching this and you're feeling a bit like I did about all things quantum. It sounds really cool, but you can't really wrap your head around it. You haven't found your way in yet. Maybe you're feeling a bit like a hapless dreamer. Well, I'm going to show you how I got here. And I'm going to show you some things that I've learned along the way, and maybe that'll help kickstart your own quantum journey. So here we go. It's been a weird path for me. I did not study quantum computing. I also did not study quantum physics. In fact, I didn't study physics at all. I also did not study computer science. I studied art. I majored in graphic design, not once, but twice. I was very visually and sonically expressive as a young person, and I was totally at home surrounded by artists, musicians, and was always inspecting and dissecting cool visuals, collecting my influences together and listening to records over and over again. And you know, all of this stuff started to translate into making things, writing, designing, forming bands with buddies. None of it was very good, but that's beside the point. Meanwhile, as a kid, I acquired this old hand-me-down computer, just like this one, an Apple II Plus. This is a vintage photo of Steve Wozniak, the designer of those original Apples. So I taught myself how to code on one of these. And as computers became more advanced, I just had to learn a little bit more and kind of level up to follow what computers were doing. So I've always had that one foot in art and the other foot in tech. And that combination of interests, art and code, led me to creative technologist roles at big tech companies like Google, Amazon, Unity, and so on. And I've also worked with renowned architecture firms, museums. I've been a guest critic and lecturer, and even served as an artist in residence in Germany for a while. And that's been my ticket to making ridiculous stuff like this. As I pause for coffee. So this is just a smattering of some stuff that I've made with friends, colleagues, and whatnot. And I'll explain how it's relevant in just a moment. Lots of data viz stuff. In those early days of data viz, virtual reality things. And there you have it. So with those amazing colleagues, none of this is just me, right? Teamwork is what makes it happen. We've won a bunch of awards and press over the years. So how did I transition from that world into quantum computing? Well, I always thought quantum physics sounded really cool, but I couldn't really wrap my head around it. There was just too much pop science nonsense in the way, and the actual math jargon was super dense. But meanwhile, check out these finger guns. This is in VR, it's a lot of fun. I'd been working on a lot of 3D and virtual reality stuff, and specifically this library for recording and recognizing hand gestures in real time. And all of that required getting really familiar with 3D math and relearning linear algebra. I say relearning, but if we're being totally honest, this was never a comfort zone for me. But I was able to push myself on it because every time I got it right, it meant I was doing something fun in VR. So there's a little bit of this positive feedback loop that was really helpful. So that's when I came across this video of Andrew Helwer and his lecture called Quantum Computing for Computer Scientists, which was inspired by this book that you see here that he's a big fan of, and now I'm a big fan of. So I'm listening to Andrew speak, and suddenly all these quantum concepts and terms were in a language that I could start to make sense of. And I realized that the math of quantum logic was really similar to the math of 3D graphics and even machine learning. So I thought I could probably take what Andrew's saying here and make a functioning version of it that runs in a web browser. And so that's exactly what I did. This is the Q.js website. That's Quantum JavaScript, Q.js. It's a drag and drop circuit composer. It's an open source JavaScript library for doing quantum simulation. And it's a modest quantum concept primer. So you can use the website as is, or you can download all the code for it and do whatever you want with it. And we're definitely going to take a closer look at Q.js and just demonstrate that this is some live interface stuff happening here. Here, we can take that. And can we throw it away? There we go. Here. But first, we should make a distinction between quantum physics and quantum computing, because I am not a physicist, obviously. So this is the zone that I'm more comfortable in. And we're being totally honest, it probably looks a little more like this, but also like this. So thankfully, I have brilliant folks to draw on. Over the next hour, whenever I say anything intelligent or insightful about quantum computing, it's because I'm channeling these characters right here. And if I state anything incorrectly or say something that's just plain dumb, it's my own fault. There are two folks in particular that I want to call attention to. And the first is Dr. Talia Gershon. She made a video that explains quantum computing to 5 levels of education from kindergartner up to expert. And that's a series that Wired Magazine does. So there's a bunch of these videos out there for different subjects. But Talia's really stands out for me. It's so intellectually challenging to make something that's this complicated seem digestible. And I really respect her ability to do that. So if you haven't seen her video, look for it online. It's great. The second is Dr. Mithuna Yoganathan. She's from Melbourne, Australia, and she has that same knack for explaining complex concepts in ways that are easy to digest. So she's made her own video series called Looking Glass View, which is a nice place to start for getting a feel for quantum concepts. And she also let me interview her for a quantum related publication that I would still like to get off the ground. So stay tuned for that. So what is a quantum computer anyway? This is a quantum computer. This hanging cylindrical tank right here. There are different sorts of quantum computer architectures like polarized photons, trapped ions, superconducting qubits. And right now, superconducting quantum computers like the one you see here are the most popular kind. They're used by companies like IBM, Microsoft, Google, and so on. Superconducting quantum computers require extreme cold to function, just a hair above absolute zero. So what we're looking at here is actually the refrigeration tank that holds the computing parts. So let's take a look inside that tank. Here we see someone servicing those parts that would be covered by the refrigeration tank during operation. And this is what some folks call the golden chandelier. So all of this intricate hardware inside the refrigeration tank is for supercooling and gently nudging the electron pairs using the quantum nature of this internal environment to represent data and perform computations on it. And here's a glamour shot of that golden chandelier. I'm told that there is some actual gold plating in here for thermal and corrosion prevention purposes, but I think what we're mostly looking at are just copper alloys. It's still very pretty. And the actual quantum computation happens right here on this tiny quantum chip itself, which sits at the very bottom of that refrigeration tank, the coldest part, right at the bottom of that chandelier. So this is where you actually nudge and measure the state of your electron pairs. And just to be clear, this hardware does not do some kind of magic. Our universe is already quantum in nature. We humans are just too big and our environment is too noisy to be able to observe those quantum effects directly. That's why we have to make this really intricate hardware that can make those effects visible to us. But like everything's already quantum. So, we're not inventing stuff. We're just trying to, fine tune and mess with it. So you might notice that this so-called computer does not seem to have a keyboard or a mouse or even a monitor. It's definitely a computer, but not in the sense that we use the term today. The way you just say computer in everyday language when you're speaking to someone, it might make more sense to think about a quantum computer like a graphics card. So if you're not familiar with graphics cards, this is what one looks like. You slot it into your computer's motherboard, and it handles all the complex rendering that your machine might need to do, all the complex graphics rendering. If you're in a high-end video games, you've probably been concerned about how powerful your graphics card is. Now, we never use the phrase graphics computer, though that's really what this is. That's the same situation we have here. A quantum computer is really this computing component, a really expensive, exotic, fantastic one. Instead of slotting it into your computer's motherboard, companies like IBM, Rigetti, Google, and so on, they hook these up, they hook these golden monsters up to the internet, and you can send them quantum computation tasks to carry out. And they'll run quantum programs and then send you back the results. So this paradigm has been around forever, right? Maybe you think of it as cloud computing or time sharing. When a movie studio like Pixar or Marvel are rendering the computer-generated imagery for their next big film, they don't just render that on a single computer. It's way too complicated, right? Instead, they'll send that task out to what's called a render farm, racks and racks of raw computing power that you can access remotely. So that's the commercial model for using quantum computers today. Unless you're at a university or major corporation building these things yourself, you're going to write a quantum program, and then you're going to send it over the internet to be run remotely on a quantum computer. And the result of that program will get pinged back to you. So that's how it works. All right. So all of that actual quantum hardware that makes up a quantum computer, that's really this intersection right here. That's actual physics and engineering in the service of creating a machine that can compute things. And, you know, I already said this is where I want to focus. No physics, just the computing part. All right. So what is quantum computation? How can you start computing things using quantum logic? Well, to answer that, you really need these 4 foundational concepts. And this is really all you need to know. And you can learn it in about 10 minutes, seriously. And then you can be your own quantum expert. So bear with me. Let's see if we can do this. Complex numbers. They come from a weird idea about multiplying. And I'll show you what I mean. All right, let's start with the so-called real numbers. I would just call them regular numbers if I were naming them. You can think of them as being on this timeline. You got 0 in the middle, and you kind of go on to infinity on one side, negative infinity on the other side. They're totally normal and not weird at all. When a real number is multiplied by itself, the product is always positive. For example, if we choose a number 2, we see that 2 times 2 equals 4. Told you this was simple, right? Similarly, if we had chosen negative 2, the product would still be positive because a negative times a negative gives you a positive result. And so that means if we take the square root of 4, for example, it's got 2 answers. Could be 2, could be negative 2. Both are right. 2 squared is 4, negative 2 squared is 4. There you go. Bob's your uncle, right? But suppose we want to find the square root of a negative number. Like, what if we try to find the square root of negative 4? Well, we know that 2 times 2 is 4. Negative 2 times negative 2 is also 4. So what gives? It seems like there's no answer here. And you're right, there is no answer. So we had to make one up. Enter the imaginary number that we call I. The symbol I represents the impossible solution to the question, what's the square root of negative 1? So I times I equals negative 1. I squared is negative 1. What if we made a number line using this imaginary number I? Let's make this one vertical, and we'll make our imaginary number line by just taking all the regular numbers that we already know and, you know, sticking I on the end of it. So we've got 1i, 2i, 3i, and so on. I think you get the idea. So now we have a solution to our problem, because we could say 2i times 2i is 4i squared. Okay, that doesn't seem like a solution yet. But 4i squared is really 4 times I squared. And we know I squared is negative 1 now. And so that means 2i times 2i is negative 4. So the square root of negative 4 is 2i. We've got an answer now. Now we can deal with the square roots of negative numbers. And why would I put you through this? Because it pops up later and it makes some pretty pictures, and pretty pictures are nice. All right, so what's a complex number then? It's just a combination of a real number and an imaginary number. So for example, we could have the complex number 1 plus 2i. So right over here, or 3 minus 4i. And you know what, if this seems complicated, don't worry about it, because the main thing here is this weird math trick that got us from a flat number line to a whole 2-dimensional graph here. So you can think of the real part of a number as being x, and the imaginary part as being y. And now you can plot all sorts of things on this graph. All right, that was complex. No pun intended. It gets easier from here. So what's a matrix anyway? It's just a grid of numbers. See, here's a matrix. We put little brackets around a matrix just to say, hey, I'm a matrix, but you can tell because it's just a grid of numbers. And it can be any size, as wide or as tall as you like. This one happens to be 3 columns wide and 2 rows high. It happens to contain the values 1 through 6, but it could contain whatever values you want. This is also a matrix, and it also contains the values 1 through 6, but it's got a different size. This one is taller than it is wide. And again, a matrix, it's just a grid of numbers, no big deal. A vector is just a special kind of matrix. So it's just a strip. It's just a strip of a matrix. So this one is a row vector because it's only one row. But you can also have a column vector. So it's just a column. It's just a strip of a matrix. So a matrix is like a grid of numbers. A vector is just like a list. And I'm not going to go into it because I'm not going to torture you further. But once you have some matrices, you can do things with them. You can add them, you can multiply them, scale them, and so on. So just keep that in mind. And if you have some matrices, you can perform all sorts of operations on them. That's the takeaway. All right, so now we know about matrices, but what's a qubit? Qubit's a quantum bit. It's the smallest amount of data that can exist, a bit is. And on a classical computer, that smallest amount is the idea of either on or off, true or false, heads or tails, 0 or 1. And that's true of a measured qubit too. When you measure a qubit, it can only be 0 or 1. But that's not the entire story, because qubits can do some strange things before you measure them. All right, so what's a qubit mathematically? It's just a pair of numbers. Every time you hear about quantum computing and people are making it sound really crazy and magical, just remember a qubit is just two numbers together. We can call the first one alpha, and we can call the second one beta. And we want to package these two numbers together so that they're always together. They're always one complete unit and never apart. So what makes this pair of numbers, so we package them in a matrix, big punchline there. And this is a matrix that's only one column wide and 2 rows tall. So it also happens to be a vector, very small one. And what makes this pair of numbers special, what makes it a qubit, is the relationship to each other. And here's the rule for that relationship. Whatever value you have for alpha, if you take alpha times alpha and beta times beta, and you add them together, it's always going to equal exactly 1. Here's a shorter way to put that. Alpha squared plus beta squared always equals 1. And that's it right there. That's a qubit. That's, you know, the magical, fantastical world of quantum computing. That's it right there. So how do you, use these qubits, whether it's superconducting or trapped ions or whatever the actual hardware is? The actual hardware doesn't matter because it all has to follow this rule. So however you choose to build your quantum computer, this is how a qubit is going to act. It's how it's going to behave. So we store these numbers in a matrix, and we know their squares must equal 1. Let's look at some examples. The most frequently used qubits or qubit states have names. It makes things easy, right? This qubit is named horizontal, and we'll talk about why it has that name in a minute. Pretty simple thing. Its alpha value is set to 1. Its beta value is set to 0. Horizontal qubit is considered 0 or off or false. It's our default starting value. Just about any quantum circuit you come across will begin with all of its bits configured this way. And we can see that these values do follow that qubit rule, right? The sum of their squares equals 1. And it's got to do that if it wants to be a qubit. If we look at the flip of this, the inverse of this, we're looking at a vertical qubit where the alpha is now 0 and the beta is 1. And this is considered to be 1 or on or true. So what does it mean? We've given them these names. We've got a horizontal qubit, we got a vertical qubit. Where do these orientation-based names even come from? Well, if we take that matrix and we take the alpha and beta and we just kind of flip them on their side and think about them as coordinates, as X and Y coordinates on a graph, that's going to be pretty useful. Let's see what that looks like. So check it out. This is if you start at the origin of the graph, right in the middle at 0, 0, and you walk out to 1, 0. We're walking horizontally out to where that horizontal qubit could be plotted. And the same thing for vertically, right? When you flip those values and you go up to 0, 1, you're going vertically from the origin. So that's pretty cool. But there's probably other qubits that follow this qubit convention that we could plot. We're going to notice any patterns there. And yes, this is where we get a unit circle. Here are some other common qubit configurations. And we can see that they all fall on the edge of this circle. And we have some named qubits. We have their opposites. And this introduces a new wrinkle here. If a horizontal qubit is considered off and a vertical qubit is considered on, then what are all those other angles about? And this is superposition. I want to demystify and de-romanticize superposition right away because there's so much pop science nonsense around this word. And let's quickly compare superposition to other states of being. If something is, that means it exists, right? And is not means not so. Perhaps something is or is not, which kind of feels close to what we want to talk about, but not quite. And here's the one that folks really get hung up on. Maybe it's both is and is not at the same time, a paradox. And sure, that's definitely a fun mental exercise, but that's still not what superposition means. Or maybe it's that, but flipped, right? It neither is nor is not, but none of that's quite right. Superposition is none of the above. It's not something that we have great words or phrases for because it's just not part of our common human experience. So I'm going to throw a quick curveball at you and we can come back to it during the Q&A if you like. Reality is a just-in-time rendering engine. Decisions are made if and when they have to be made. Otherwise, it's all superposition. Anyway, that's getting a little far from the math. The math is what tells you what superposition really is. Let's just look at what those alpha and beta values actually mean. And here's our good old horizontal qubit with its 1 and 0. And what that alpha slot actually means is when we measure this qubit's value, how much do we think its value is going to be 0? Conversely, the beta slot means when we measure this qubit, how much do we think its value is 1? And our horizontal qubit is voting 100%. It is all in on the outcome being 0. And so that's why we consider horizontal qubit to be 0 or off or false, is because it's put all of its eggs in that first basket, in that alpha basket. It's like it's gonna be 0. And a vertical qubit is just the opposite. It's got no votes for 0. It's put all of its votes in for 1. And that's why we consider it to be 1 or on or true. So a qubit is really a declaration of probability. What's the probability of a particular outcome? And if we look at a perfect superposition like this one, it's really sweet superposition here, take my word for it. And we actually square those alpha and beta values, both of them are 1 over the square root of 2. What happens if we square those values? Well, the alpha value is voting a 50% chance that the outcome will be 0, and the beta value is voting a 50% chance that the outcome will be 1. So it's an even split. Superpositions don't need to be an even split. In fact, quantum circuits often nudge these probabilities slightly in one direction or another. So you can think of superposition as being any qubit state that doesn't have a 100% vote for one given outcome. All right, so let's throw in one last wrinkle before moving on. Remember how we talked about complex numbers? Well, a qubit's alpha and beta values can actually contain complex values. And that adds a whole other dimension to our qubit. So suddenly plotting a 2D circle like this isn't enough. We need a 3D sphere to demonstrate all the possible states that a qubit can occupy. So enter the block sphere. And that's block B-O-L-B-L-O-C-H, named after physicist Felix Bloch. Let's check out our familiar horizontal and vertical qubits here. And here we can actually take this and move it around. That's our horizontal qubit. And you can see that it's got a little, let's call it a flag up at the top. And we can move that down to the bottom. We can see that our vertical qubit is all the way down at, we'll call this 1. So this is the value of 1, and that's on, and now horizontal is off. So those are our two opposite states, right? On, off. But then we have all this other stuff in here. So this is where, if we measure the qubit, we have a 50% chance of it being on or 50% chance of it being off. And we can actually kind of rock around the clock here. These are all actually sharing that same measuring probability. These are all 50% on or 50% off. So what makes them different? And what makes them different is just the fact that their phases are different, that they're moving around the block sphere. And even though they have the same probability of measure, they can mean something different computationally. You can use them in your software, in your quantum software, to do slightly different tricks. And you can think of these phase differences as like musical timbre, where the note of two different instruments might be the same, but they sound different, and you can use them for different things. So just to drive that point home, so what's timbre? It's the quality of the music note being played. For example, imagine composer Tamika Reed playing a middle C on her cello. Right, you can hear that she draws the bow across. Now imagine Yolanda Brown playing the exact same middle C, but on her saxophone. It's the same note, but it sounds different, right? So that's one way to think about these phase rotations here. I just love this. I love playing with these diagrams here. They represent the same note, so to speak. It's a superposition, but we can write quantum programs that make use of those individual phases. All right, this is the last piece of the puzzle, and it is much simpler than qubits. A logic gate is a means of transforming a bit's value. One of the simplest logic gates is an inverter. It takes a bit, flips its value, so on becomes off and vice versa. And you can think of a quantum logic gate as just a matrix. So here's one right now. It's called a Pauli X gate, Pauli named after physicist Wolfgang Pauli. And the X part refers to the fact that this gate causes a qubit to rotate around the x-axis on that cool block sphere that we were just playing with. So just keep in mind that if you have some matrices laying around, you can do things with them, like multiply them together. And that's how you transform qubits from one state to another. So here you can see it flips the horizontal to the vertical. Here's a fun gate, the Hadamard gate. This gate flips a qubit into or out of superposition. So you can start with horizontal gate, and then, horizontal qubit, multiply by a Hadamard gate, and then you're in superposition. There are many sorts of quantum gates. If we had more time, we could nerd out over the fact that every quantum gate is its own inverse. So if you apply it twice in a row, it's the same as not applying it at all. That's kind of a cool computing concept. But I think we're ready to start juggling qubits and gates together. And to do that, we're going to need a new interface. Okay, so now you have all those fundamentals you need to get cooking with quantum. And it's okay if you didn't pick up 100% of that the first time through. It's in your head now, I promise you, I promise you. All right, so we're about to build some quantum circuits together. And quantum circuits are represented by diagrams, kind of similar to musical staves. When a musician reads a line of music, she begins at moment 0 on the left edge and proceeds forward in time by reading to the right. And in this example, we can see from the ornate figure on the left there that the pitch of the notes will be described by a C clef, and that each measure will span 3 beats, thanks to the 3/4 time signature notation there, right? Shout out to fellow musicians. Similarly, quantum diagrams, quantum circuit diagrams, are a series of moments in time, beginning at moment 0 on the left and proceeding forward in time by reading to the right. And here we have a quantum circuit that is 3 moments long and operates on just 2 quantum bits. So if we start at moment 0 there, both of our quantum bits are set to 0. They're both horizontal qubits. And in moment 1, we apply an H gate, a Hadamard gate, and that flips that first qubit into superposition. So now it's in that funky state where it could end up being 0 or 1 when we measure it. And then in moment 2, we do something even crazier. This is a hint of entanglement here. This is a controlled NOT gate. It says if this qubit is really going to be a 0, then we're not going to do anything to the second qubit. But if it's really a 1, if it's active, then we're going to flip the second qubit to be active as well. And then in moment 3, just for fun, we flip them both using a poly X gate. So the outcomes can either be 0 and 0 or 1 and 1. So now we're ready to peek at Q.js and its quantum circuit composer interface. It's a drag and drop circuit composer, as well as a code API. And I realized that I made a pretty decent explainer video of this at some point, and it shows off how these interface bits work together, but I've never shown it publicly before. So I'll roll it for you now. It's just about 2 minutes, and it gives me a chance to have a drink of water. So here you go.
Okay, all right. Quantum JavaScript, it starts off with this interactive circuit building interface that runs right in your web browser. And I'll explain what these things are in a moment, but I'll just show you how it operates first. We can select everything and throw it away and start over. We also have an undo button here, which is great, and also a lock button, so we can lock our circuit and can't mess it up, can't select things, can't throw stuff away, which is even more helpful on a mobile interface where there is no hover state and selection. You're tapping, perhaps you're tapping to scroll, perhaps you're tapping without meaning to, and you definitely don't want to mess up a circuit that you've carefully composed. But in this case, we can throw down an identity gate and maybe a poly X gate and select them and combine them together to make a controlled gate here. And what we've just created here is a bell state. And even if you don't understand any of this stuff, you can see the live probability results being updated in real time as we change things. So it's really cool that you can drag and drop stuff together, but you can also code things, code the circuits with JavaScript. And what's even more than that is you can combine the two. So if we open up our JavaScript console here, let me clear it out. It says that this circuit is accessible in our console. And so let's give that a shot. Let's see, we get a circuit back. Here, let's make this a little larger. Let's see what that circuit looks like. We can get a diagram of it. It's not very interesting when we have a blank circuit. But here, we can quickly build that bell state again. And you can see as I'm editing the circuit, we're getting real output just like that. And here, let me scroll up. So we can actually see that this ASCII diagram looks very similar to what we have right here, doesn't it? And so that is pretty cool. And what's even cooler is we can start to do things like, let's say we want to add another one of those H gates, right? That's a Hadamard gate, and we'll talk about that in a second. Let's add it to moment 3 on wire 3, which should put it right there. Let's see if we can do that. Oh, and there it is. So we can actually jump back and forth between code and the drag and drop interface. So it's not about dumbing something down, not at all. With Q.js, you have access to this quantum circuit both through code and the drag and drop interface, and you can fluidly switch back and forth to whatever has least cognitive overhead in that moment. Let's say I need to get rid of everything here in moment 2. I could certainly code that, or I could just select it and throw it away, right? So I just want to emphasize that designing a user interface and offering pictures to look at and click on is never about dumbing something down. It's about making tasks easier and more efficient for us human beings who require that.
All right. So here's the thing about quantum entanglement, which we saw a little bit of there. One qubit on its own is just a single note. I can have timbre, but does it really have emotion? I'll show you what I mean. So here, let's see if I can do this live. Here's a C major triad. Can we do it live? Oh, you know what? Something about the screen sharing is not letting us do it live, but that's okay because I have a backup. So what I was going to demonstrate is that 3 notes together can make a triad, and it can be like a major chord, let's say a C major chord. And it has sort of an upbeat, friendly feel to it. But you could change just one note within that chord and make it a minor triad, which has a bit of a sad feel to it. There's nothing particularly interesting about the frequency of the one note that I changed. I mean, on its own, it doesn't really mean anything, but it's about the relationships. When they come together, it means something as a sum that it didn't mean with the parts. And here is a little bit of a demonstration. I think you'll recognize the song. And here comes that, here's the C major, and one note's gonna change. And now it's a minor. And at the risk of driving it home, here it is one more time, the major, and then that minor chord. So that's just a hint at how entanglement and how quantum computation, once you're running it all together, the state of the whole computer relies on each piece. And that's part of what makes it really difficult to simulate on classical computers, because classical computers are just not very good at this. All right, so we've gone deep on some of the fundamentals, complex numbers, matrices, qubits, and gates. And now we're really here, we're really just beginning to play with actual quantum circuits. But for this, I'm just going to do a very light touch. You now have the mental tools to start exploring both Q.js on your own and quantum circuit diagrams in general. So I'll just re-emphasize this one feature here, where you can generate your own quantum circuits just by typing in characters. And so let's see. This text here has generated this circuit here. And you'll notice this circuit is 4 qubits, but we could just, let's say we want to add 2 more. And so now we have more here, and we can start to change the circuit. And as we're changing the circuit here, it is also changing the text here. So that Hadamard gate that we moved, or that polyx gate that we added. So you can use this to start building quantum circuits of different sizes. And if you want to get into the code, you can start doing custom gates and things like that. But I think that's a good enough taste for right now, and we can keep moving on in the interest of time here. Shor's algorithm, this is a means of efficiently factoring composite numbers into the prime numbers that make them up.
It's 11 hours.
It's sort of a shortcut. Ooh, and I'm realizing the time, but it's a good thing we're near the end. You can cause a guitar string to suddenly vibrate as 2 smaller parts instead of its full length, just by finding the octave harmonic. And this is different than just pressing down on the string, which causes only half the string to vibrate. This is a very light touch that leaves both halves of the string now vibrating independently. Could you hear that little bit of an octave jump when you just lightly touch? And that's kind of like what we're doing with factoring and with these modular processes. Maybe we'll have some time to Q&A some of that later. All right, like I said, I see the clock running, so let me jump to one last interesting feature of Q.js. I happened to be working at Amazon at the time that I finished the first working version. And Amazon just so happened to be working on a quantum service called Amazon Bracket. So like, what are the odds, right? It was just in the air. So here's me narrating a demo where Q.js could drive actual quantum hardware via Amazon Bracket.
So here I have a Jupyter notebook with Amazon Bracket loaded, which means that I can use Python code. Bracket is a Python library, and I can use that to build quantum circuits that I can then run on a simulator in the cloud, or I can run on quantum hardware, because Amazon has partnered with different quantum hardware vendors. And so we can do that, we can offer that to our customers, and that's pretty exciting. But what's also exciting is this. With just a few lines of HTML, really 2 lines of HTML, I can inject Q.js into this Jupyter notebook. It's now injected, and now I can inject my quantum circuit composer. And this composer, which should look awfully familiar, is writing bracket code. So this is actually bracket Python code, which right now is set to run on the simulator in the cloud so that we can get quicker results. But if you wanted to, you could switch what device we're running on, and you could actually run this on quantum hardware and get true quantum results. So check this out. Down here you can see where it says our Q.js circuit equals a new circuit, and it has a placeholder identity gate. This is bracket code, and we're about to watch it change as I start to compose stuff. Look at that. Look how it put a Hadamard gate and created a C0 gate. And we can take that and we can run that. What this is a coin flip circuit. And we're waiting for the output to come back from the cloud. So Hadamard puts the qubit into a state of superposition, and then this distributes that superposition to the qubit on the second register here. And so our two possible outcomes are 0, 0, and 1, 1. And you can see we've gotten a result back from the simulator. It's run that simulation 100 times, which is a customizable number. And it's come back roughly even. 54 times it came out 0, 0, and 46 times it came out 1, 1. So here's the deal. We can drag and drop and build circuits as we please using the Q.js drag and drop interface. We can even edit that thing and get real-time reports in the JavaScript console still. And it is building Amazon Bracket code, which we can run on a simulator or on actual quantum hardware. So that is pretty cool.
And it was pretty cool. This is something that I was demonstrating inside Amazon before Bracket launched, before their API was final. Their API did change a bit at launch. And so it stopped working. The demo stopped working because Amazon changed their API. And I know Philly ETE is remote this year, but if we ever do meet in person, buy me a drink and ask me about the head of Amazon Quantum and how he absolutely wanted Bracket to launch with the Q.js interface, angrily so, yet wouldn't bring me onto his team in order to make sure that it happened. So it's been a few years now, and they still can't manage to add a graphic user interface. Amazon, amateurs. I'm just ribbing you, sort of. All right, so what lies ahead for the world of quantum computing? All right, quantum computers right now are really noisy. I don't mean that sonically, although that's a good analogy. I mean, they're very error prone. It's hard to ensure that those qubits will maintain their integrity during the life of a quantum program. And the more qubits you add, the worse it gets. So making reliable quantum computers really is an uphill climb. But money and brain power is being poured into this, and it's a well-known problem. People are working on it. So stay tuned, be optimistic. Good things are coming. Quantum supremacy. That's the state where quantum computers finally have enough qubits and noise reduction that they can actually outperform not just a classical computer on its own, but classical computation in general. Google's announcement that they've reached quantum supremacy was sort of like a kid asking a genie for infinite wishes. Like, okay, but that's not the point, right? So the quantum algorithm that they used really didn't make sense for a classical computer. It's not really a great comparison. We want to see real quantum supremacy with things that we care about. And that lies in the future, and probably not the too distant future. So quantum computers, why bother, right? They're expensive, they're weird, they're not intuitive. The reason to bother, all sorts of industries are going to be blown up by this computational power. Machine learning, right? The math behind machine learning maps very well onto quantum computing. So we could create more sophisticated machine learning models more quickly. They could solve more complicated searches and other problems. Finance, super fast, complex forecasting, and the ability to search and sift through that data. Quantum computers are very well poised to handle that better than classical computers. Simulation. Nature itself is quantum, right? And it's difficult for us to simulate it. But with a quantum computer, it's more of an apples to apples problem. So it becomes simpler. And security. Potential to break certain encryption schemes, yes, that's on the roadmap, but not anytime soon. And that's due to the number of qubits that you need and the noise reduction, but it will happen someday. So that's pretty interesting. And if I were to speculate, just like blue sky for a bit, maybe we're 20 years out from practically useful for government ideas, quantum computing, and maybe a little longer for it make sense for commercial activity. And maybe in like 60 years, quantum computing will just be cheap enough and practical enough and ubiquitous enough that everyone is making use of it in their own daily lives and no one cares. The same, and that's the victory condition, right? Is it's just so widespread and ubiquitous that no one cares. Just like smartphones in your pocket. That is a ridiculous amount of computing power, and we just, use it to play Candy Crush. All right, and I'll end on the future of Q.js. It's really, I've had potential investors chat me up and other kind of commercially minded folks, and they seem to be blown away that I do this for fun. But it is fun. This is very weird, the way that our universe actually works. And to be able to taste a piece of that is really cool. I've got a whole list of features and fixes I want to implement. Right now, I'm rewriting the internals to take advantage of the brand new WebGPU compute API. So you get hardware acceleration for your simulations. And this is all where I could use your help. Q.js is open source, it's on GitHub. If you like JavaScript, if you like quantum computing or the idea of quantum computing, you can jump right in. There are open issues you can check out, ongoing discussion that could use your voice. There's a lot of documentation, it's easy to get started. So what have we learned, right? This is what a quantum computer looks like. Most of this computation stuff is really just juggling matrices. And Q.js lets you use a drag and drop interface to pull circuits together, and then you could use that to drive real quantum hardware if you want to. Quantum computers can solve certain complicated computing tasks that are too complicated for normal classical computation. It's still early days, but once these machines begin to really flex their muscles, it will change the computing game forever. And reality is a just-in-time rendering engine. All right, folks, that's it. This has been Quantum Computing for Hapless Dreamers. Sorry that took a little long. I'm Stewart Smith. That's my name at the top there. Second line is my URL. You can find out about more about me, other projects, links to Q.js, links to the Q.js GitHub, all that good stuff. All right, I'm excited and a bit terrified to take a question.
Thank you very much, Stewart. I see that there's a couple questions in the Zoom channel. Do you want me to hand them off to you?
Yeah.
All right, so one, I think you touched on this in your why bother section, but one of the questions is along the lines of the, oh, I'm sorry. The first question here was, what are some real world applications? This seems to be very low level stuff. I mean, you touched on that in your why bother section, but is there more that you want to speak to about that?
Yeah, search sounds like a boring thing. Didn't we already solve that? But not so. If you have a huge you of things that you need to sift through, and they could be very important things, like maybe we're trying to design a new vaccine that has to pay particular attention to certain DNA sequences. Man, DNA is big, and it's difficult to search through, and find patterns within. Quantum computing turns out to be very efficient at search, particularly when things are in kind of funky orders and whatnot. So without going into the math of it or trying to demonstrate the search algorithms, it turns out search is not as efficiently solved as we would like. And quantum computing will allow us to take these things, searches that would take days or a lot of classical computing power, and reduce it to something as easy as a Google search, right? So that's one way. At some point, security will become a really interesting concern because quantum computers, not now, but at some point will be able to do really efficient factoring in the prime numbers, which is the basis for a lot of the digital security that we use today. So does that start to answer a little of the why bother?
I definitely think so. The next question is very similar, so I'm going to skip over because we've only got about 2 minutes left. This question is about in reference to the coin flip demo. Yeah. Can you explain, even at a high level, how to apply a quantum circuit to another specific simple problem?
Oh, yeah. Well, random numbers can be part of security. Like if you're trying to assign unique IDs to something, that could be as boring as unique barcodes for different products. You can't have two that have the same ID, but you want to be able to pick random numbers so someone can't guess a barcode ID. And so something that you could do that's very, very simple is use a quantum computer which has real quantum randomness. This is not a pseudo random number generator. This is really harnessing the universe's own random number generator. You could just have a bunch of those Hadamard gates that randomly flip bits. And at the end, let's say you have, 1,000 of those, or 1024 even. At the end, you have a totally random number that can't be predicted ahead of time. And if you go deep on security, you'll find that different companies have had trouble where it's turned out that their random number generators were not quite as random as they had hoped. And it allows an attacker to start to narrow down the number of possibilities that they need to try to defeat that security. So is that, did I answer that a little bit there? Practicality of a practical use for a coin flip circuit?
Definitely. All right, so I think we've got about a minute left and I don't want to suddenly cut out. So if you just want to say a few parting words, thank you so much, Stewart. Really interesting talk and we appreciate you being here. And I guess hopefully you can participate in the Room B chat. I think there's a couple other questions that you didn't get a chance to hit.
Oh yeah, for sure. I'll stick around there. So thank you so much. This was really fun.
Thank you, Stewart, and thank you everyone for attending.